Hello, good morning, or good afternoon, depending on where you are in the world. This is Andrew Ma here with RATS, and we are here with our 5th Technical Sessions webinar. We've got a great topic here today, and Karl Blackmore from ABB is going to be our presenter today. Just want to mention, registration has been increasing, so thank you for everybody for spreading the word and for your interest. This one, actually, we've had our most registrations to date. And if you're not able to attend, of course, the recordings are available afterwards. I want to mention, too, that we do have some upcoming webinars to be scheduled from MAN Energy Solutions, Alberta Governor, NanoPrecise, Corrosion and Abrasion Solutions. That'll be going into next year. So let us know if your company is interested in providing a webinar at a future event. I'll hand it over to Ralph now, who's going to give us our introduction for our topic and our presenter.
Yeah, I also I'd like to welcome everyone to our technical presentation. My name is Ralph Dickow, and I set up these presentations. And just go a little bit of housekeeping. Your microphones will be muted. I'd like to get your questions for Karl, and you can send those in via the questions tab. You'll find that in the control panel. We'll have questions and answers at the end of the presentation, and there's additional information for you attached as attachments about today's presentation. More technical information there, and some information from ABB. And you can download those, and they'll make a good additional resource to today's webinar. Please hold on after the end of the presentation. There'll be a survey come up, and we would like to get your feedback. Our next presentation date, and they're always the third Thursday of the month. It's October 15th. Check our website for updates for what will be presented. I'd like to introduce our guest speaker today and not take away from his time. Karl Blackmore is a veteran in the electric motor, induction motor industry. He originally trained as in the mechanical field, but went over to the other side and took additional education in electronic engineering. That was at Bristol Polytechnic in UK. You'll recognize that connection from his accent. He's been working in Western Canada since 1993, and he's experiencing with a variety of applications and industries, oil and gas, HVAC, mining, and process. So yeah, lots of experience in different areas. So looking forward to getting an introduction and very interesting information on electric motors. Thank you, Karl.
Great, thank you. I'm just going to show my screen. Okay.
That's your presenter mode.
Confirm that it's coming through as we talked about before.
This is your presenter mode.
Yeah, great. Thank you.
Yeah, you need to switch over to audience view.
Yes, that's one.
Okay, just 1 second. Okay, well, thank you, everyone. Thank you for the kind introduction. As Ralph said, I came through this world in the mechanical field. Most of the time I spent vast majority of my career working in fluid handling. So I've always been around pumps and pressures and gas and liquids and stuff like that. And when I moved to Alberta with the oil and gas industry, found that some of my previous experience lended well to the industries here. And I always had an appetite to be in the electrical field. So during my career as a service technician, I was always working on electronic equipment, and so I went back to school to augment my mechanical career and add some electrical experience to it. And during that training in England, we always had electrical classes as part of our mechanical training anyway. So without further ado, there's some material here I'd like to share with you. And I know there's going to be some feedback questions later after my presentation's over. And for all of you sitting at home, I hope you fill in your survey to the catering committee and let them know how you enjoyed your lunch today. That's my humor for you. That's my British humor. I hope you appreciate it. Anyway, the agenda we have today is going to be fairly high level. So I see this very much as a high overpass of the electric motor business, because I see there's so many little segues and rabbit holes that we can go down. So hopefully this appeals to most people in the audience. Hopefully it's not too rudimentary, not too heavy for some people. But we're going to talk a little bit about the some simple theory around motor theory, and I'm going to get into some of the mechanics of electric motors, particularly about different types of enclosures that we'll see in industry. We'll talk a little bit about what you might see on a nameplate and what the difference between synchronous speed and what slip is, understand the torque relationship. Then we're going to get into the things that tend to affect most of us in Alberta, and that would be temperature ratings and insulation classes. We'll segue into some of the differences or nuances between the National Electrical Code and the Canadian Electrical Code on Class 1 and Division 2. I'll wrap up with a fairly high-level overview of what some of the differences are with a VFD rated motor and a VFD duty motor. And typically, what I'm going to talk about is mostly at the lower end of the horsepower, but this could apply up to about 2,500 horsepower. We definitely won't be talking about synchronous motors. As I said, it's a broad topic, and there's so many different avenues that we can go down. So what is electric motor? So essentially, electric motor takes electric motor and converts it to mechanical power. So typically in most applications, the customer or the end user, what do they want? They want torque and speed. That's really what they're after, how that's produced is not a lot of people's concerns, but really what we're trying to do now is get rotating power and control that speed. And I don't know if you heard this stat before, but in industry, about 60 to 70% of all the power generated in an industrial plant is consumed by electric motors. I know when I'm out socializing just in normal events, people ask me about motors, and a lot of people outside of our field probably don't know where motors are, but they're everywhere. They're absolutely everywhere. If you look at a hospital or an airport, they're all over. In air handling units, there's so many motors and so many applications. So this is probably the heaviest slide that I have, and we could go into all kinds of theory about what makes a rotor turn, but essentially we're talking about AC induction motors. So an induction motor is using permanent magnets and electromagnets to turn a shaft, and the rotor is the rotating part, and the stator is the stationary part. The stator has the electrical wires that wrap around in coils, and when a voltage and current is applied, that induces a current and a field into the rotor and causes that rotor to start to turn. And that the reason it turns is that through AC current, the north and south poles of these electromagnets are alternating. So you start to get this cogging effect, and as you speed up, it becomes more and more smooth. And depending on the number of windings and slots, you can get a very, very smooth output. And so, like I said, that last slide was what they call the left-hand rule, and it talks about how you get flux and what's induced into a motor. This drawing here, or this graph here, is an important one to study for a few minutes. basically on the x-axis or the horizontal axis is our base speed from startup. So when you initially apply a voltage or a current to a motor, it's going to go through a ramp up position, and as it increases in speed to that 100%, this is what we call the rated speed. And as it's going through that cycle, a different amount of torque is generated. So the red line generates the speed torque curve. And so there's four bullet points here, or four notable points that's in this curve. And the base one is what we call lock rotor torque. So when the rotor is stationary, or the driven load is not moving, this is the amount of torque that's generated before you get that initial amount of inertia. So that's almost like thinking about the old days when you'd have to, when the old stick shift cars were, and you had to jump start something, you needed a certain amount of torque to get it moving. So a certain amount of torque and current is applied to get that rotor moving from its initial standing place. And as it moves through that speed, there's a low point called a pull-up torque. So that's the lowest amount of torque that is generated. And as it starts to get closer and closer to rated speed, you get on this curve a high point, which is called the breakdown torque. And anything on the right-hand side of that breakdown torque is what is the maximum torque that you will get out of that motor. If the load or the application requires more than that torque, you can run into a stall condition. So if you have a very, very heavily loaded conveyor or something that's not sized correctly, an application type issue, and the motor can't generate that torque, it may start to move, and then it will stall and typically trip out on an overcurrent, or some other device will trip it out. And the last point is what we call the rated torque, or full load torque. And that's somewhere just offset from the 100% speed. And I'm going to talk a little bit about synchronous speed versus slip. But this is what we call the NEMA design B curve. And it probably makes up for 95% of all the applications that you would typically run into. And on that point, there are other curves. There are other NEMA design curves that go through A, B, C, and D. And this presentation will be available as a handout in PDF format. But like I said, the B curve is the most common. That's almost 95 times out of 100. You're going to get that type of design. And there's a lot of colors on here, but there are other designs. There's a D, which is usually has a very high starting torque because of things like hoists. So there are unique applications that have completely different speed torque profiles. And the black line at the top that sort of intersects around about the 600 point, that black line is the current. And that current is from stationary to operating speed. And there's a normal value, and this is part of the NEMA MG1 design standard, that on a low voltage motor, you're typically looking about what they call an inrush current of about 600%. I'm not sure if everyone normally gets their head around that, but if you have a 100 horsepower motor of 575, and we'll talk about this in another slide, that's typically 100 amps. But when you're talking about 600% starting, this is where the electrical design engineers have to do their calculations to know how many of these electrical loads are coming on at once, and they have to provide enough power through the utility to start all these loads. So if you have 10 large motors all being turned on at the same time, you can get a flicker situation, or even a complete blackout where you overtax the grid or the transformer and it goes into a shutdown. And if you haven't been around this concept before, you will see it happen many times in all of our commercial buildings. When the AC kicks in, you may notice that the lights flicker. and that's because of this inrush current. So 600% inrush, and then you get you're moving to the 100% current, the full load current at normal operating conditions. So in typical, I've put this slide together. We're going to talk about just an overview slide. There's not a lot of detail in here, but there's obviously globally, there's two types of electrical systems. In North America, we work on a 60 hertz, so 60 cycles per second is our generated frequency. And in many other parts of the world, they generate their power with 50 hertz. So, and there's a number of different voltages. So in single phase, that's one wire, typically one utility wire like you have in your home, that would either be powered at 115 volts or 230 volts. And in Europe, there's a large combination of 50 hertz single phases. As was an introduction, I'm from the UK, but we don't have 110 volt systems in the UK. We usually start at about 220, 230. And I've been here for 30 years, so I don't consider myself to be British anymore. Definitely relate to Canada. On the three-phase side, 60 hertz can go anywhere from 208 up to 13,800 volts, so 13.8 kV. In our industrial plants, we're talking often about 4160. Depending on the age of the plant and the infrastructure, there may be some 2.3 or 2300 volt supply systems, and we don't see too much request for those motors anymore, but they definitely exist, and they're still very much available. And just to wrap up on the last line, in the 50 hertz world, there's a combination of voltages there. So hopefully that makes sense. If you're definitely in the manufacturing business and you're exporting, you will see requests for these types of voltages. There's a little bit of theory here, and hopefully it'll be fairly easy to follow along. We talk about synchronous speed. So when most people order a motor, they're going to ask for, I want a 3600 RPM motor, I want a 1800 RPM motor. And because slip is an important function for motor to generate torque, you're always going to get something slightly less than synchronous speed. And in the case of what I've identified here as a two-pole motor, it's not unusual to see 3550 or somewhere thereabouts on the nameplate of the motor. In the real world, it probably is fairly insignificant if you're doing calculations on gearboxes. We're talking about small percentages of speed differential. And if you see larger slips or larger nominal speeds or asynchronous speed, that could often be an indication of a higher torque motor. And in this sort of simple calculation here, the way we arrive at those speeds is we look at there's a constant of 120 times the frequency, whether it's 50 hertz or 60 hertz, by the number of magnetic poles. And that's how we know. We can talk about someone says you'll go and put an order in for a 4-pole motor. We know that's going to be an 1800 RPM motor. Like I said, the slip is something that's really critical to motor performance. So, I mean, it's a simple calculation. Basically, your normal speed, or no low speed, which would be your synchronous speed, with the operating speed in this example, there's 2.78% slip. I don't think I need to dwell on this slide. Now, here's a general rule of thumb. I'll try to give you some nuggets that might help you with your day-to-day calculations. So when we're talking about why would we have a 2-pole motor? Why would we have a 4-pole motor? Why would we have an 8-pole motor? Well, as I said, with the number of poles, as you increase the number of poles, you increase the amount of active material. The motor becomes a lot heavier, a lot more beefier. a lot more torque here. So in this example here, there's a simple rule of thumb of these are guidelines, not necessarily hard and fast numbers, but you're typically going to get about 6 foot-pounds of torque per horsepower on a 8-pole motor. So again, this information will be provided to you. And if you know one of those values using that simple calculation on the bottom, it's easy to cross convert. If you know what torque you need, you don't know what size motor to buy, you can use this formula here. And in the formula on the right hand side, it might turn around and you might calculate something that says you need a 32.6 horsepower motor. Well, then obviously you're going to go to the next size up and buy a 40 horsepower motor. And the 5252 is a constant, and that constant applies to feet-pounds. So if you have Newton meters, there's a different formula, and that information is readily available through multiple sources. Another rule of thumb, which is another fairly good, reliable guideline, is so how many amps per horsepower. So in this example here, I've given you the most common voltages that we use here in North America, particularly in Canada. Obviously 575 is very rare in the US, although they do have it in some of the areas where they have textile mills. It's an anomaly. If you go down to Georgia, there'll be some textile mills that still use, or not still, but do use 575 volt motors. But that's one of the challenges we have in Canada, is that often the availability of 460 volt motors, there's a lot more common, a lot more inventory to pull from on 460 versus 575. But in this example, general rule of thumb, you have a 600 volt supply or a 575 volt motor. It's really, really simple to say, well, that's 1 amp per horsepower. In my early example, I talked about 100 horsepower, 100 amps. And as you can see here, the 460 gets 1.25, 230, 2.5. So I think this is good stuff to put in your back pocket. If we were meeting in person, I would have had some booklets to hand out to you, but there are a number of sources where this information is available. So moving into types of enclosures. So typically motors fall into 2 categories, what we might call open circuit or closed circuit. And what I mean by open and closed circuit is a closed motor is basically, for all intents and purposes, excluded from the outside ambient atmosphere or outside air. An open motor, actually part of its cooling is to take the ambient air and pull it through the motor and exhaust it through the motor. So any particulates or contaminants will see the internals of the motor. And I'm going to show you some other examples on the next few slides, but it doesn't mean they're bad. It just means that you may have some more maintenance and you may have some more contamination. The workhorse of our industry in mostly low voltage motors is TEFC, and I've used a bunch of acronyms here that we can go through. But a totally enclosed fan coil motor basically is a enclosed motor with a shaft-mounted fan, and it pulls motor actually from the non-drive end over the motor body through to the drive end, and that tend to be a lot less maintenance, and they tend to be the workhorse. Now, people ask you, when do we transition from a TFC motor to an open motor? And it's going to transition often differently between manufacturers, and sometimes that's an economies of scale or manufacturing capability, and it may even be customer preference. It could be part of the hard spec. As you move up into larger frames, you may start moving into totally enclosed air-to-air cooled or totally enclosed water to air cooled. And there's also abbreviations around force ventilated and assisted separately ventilated or blower cooled motors. I'll show you some examples. So this slide here, hopefully it's visible to most people. These are all open motors. The one in the bottom right-hand corner with what we would consider an ODP, open drip proof. It has really no protection from the outside atmosphere. And in very crude terms, this is the style of motor you may see in your home furnace. So your furnace fan motor typically would be an ODP. It's inside, it's pretty much controlled environment. It's not really a problem. The top left-hand picture is shows some assisted fans. We call these piggyback blowers. So, and you'll see these separately ventilated or fan assist or blower cooled motors in applications where the motor is either running in a very hot environment or most predominantly when you're on a VFD and you're starting to use a much slower speed range. And typically, as we're relying on internal fans or external fans to cool the motor, we're running that motor slower and slower and slower. It's not getting the same airflow over the motor, so the piggyback blower will continue to blow constant speed air over the motor. The picture in the top right, I'm going to segue into another slide. This is what we call a WP2 motor. So this is a picture of a WP2 motor. This is the workhorse motor of our industry. When I say our industry, I would assume that most people on this call are probably dialing in from Alberta and may at some point in their career been associated with the oil and gas industry or other heavy industries like pulp and paper or forestry. A WP2 motor stands for weather protected. 2 is like a higher level than 1. It's widely accepted in industrial plants for outside use. And the significant differences with a WP2 is the sort of the second bullet point. There's the outside air, as I said in one of my earlier slides, is brought in and is used to cool the internals in the motor. So that outside air goes through a filtration system, but with a WP2 motor, it has to make at least 3 minimum 90-degree bends. And part of that is to knock out particulates. And the bullet arrows I've put on here just show you at the bottom. Sorry, let me go more to the middle. On this one, you can't see it because of the angle, but there'll be a mesh underneath the arrow that says air inlet. Air is brought in from underneath. It goes through a filtration system. In this photograph here, there's a little hinge. There's a piano hinge with a couple of screws to lift that hinge up and take out this galvanized or stainless steel filter for cleaning or replacement. And then the motor goes through, the air goes through a pathway. Some are called unidirectional, some are called bidirectional, where it depends how the airflow is, but it's exhausted out through that bottom vent. And I just thought in this photograph, because it's in the picture, I'd just show you how large terminal boxes can be. So this motor would typically be for a petrochem application with something called an API standard. So they have very, very large terminal boxes because of some of the extra protection equipment that goes into the main terminal box. Moving on to our enclosed motors. So both of these examples are TFC. So rip-cooled motors, these are cast iron motors. And then again, different companies make transitions to frames at different sizes based on either their economies of scale or manufacturing capabilities. And I already talked about fan assist or blower motors. The one in the left-hand corner shows you the blower assist. And again, this is what you're going to find on a VFD type driven load. And it depends. I should be clear that not all VFD motors need a fan assist. It really is for very low speeds. Getting 2-to-1 ratios and 4-to-1 turn down ratios is not usually a problem to add additional cooling.
Karl, just to let you know, it's 12:30.
Okay, great, thank you. I'll just move on fairly quickly on these ones. I just want to show some other examples. There may be some questions after about explosion-proof motors, but in the rest of the world, other than North America, they don't actually call motors explosion-proof motors. They actually call them flame-proof motors, which is a more accurate description. And there's no such thing really as an explosion-proof motor, because when you have a rotating part moving through a hole, you cannot guarantee that some air or gas won't enter that motor, especially if it's standing still and it's sort of self-aspirating, or pressure is at equilibrium. So yeah, just to show, the main thing here is about the size of the fits, and basically if there is a detonation, that those motors will, the detonation or flame is extinguished before it reaches the outside atmosphere. There's just a couple of examples here. When we're talking about mountings, there's C-face, D-flange, and our company sells a lot of P-base motors. So these are often used in vertical pumps. Just some key components that go into a motor. As I mentioned earlier, there's two major parts of a motor, and that's the stator. The stator is usually press fit and welded into the frame of the motor itself, and that's where the electrical current is passing through. On the right hand side, we have a rotor and shaft, and this one shows a cast aluminum rotor with those cast fins. Those fins are there by design. It's actually part of air movement. And you may not see, because of the quality of the picture or the size of the picture, there's little knobs or little lugs on that motor, and that's where balance weights will often be placed. I like this picture personally. I always like cutaways or exploded views. This one shows you a typical large motor, separated, and the difference between the blue font and the red font is the blue font is just mechanical parts to hold the motor together to do work. The red font is what we call the active material. So the active material is where current has been done. When you talk about electrical steel, that's different than regular steel. So this has a lot to do with the efficiency and the quality of the motor. So this is where your power factor and efficiency gains are done with what we call the active material. And this is sometimes where some of the losses happen. Just moving along fairly quickly here, just a little of a breakdown of what you might see in a typical low voltage motor. This wouldn't be every single motor you'll come across in the field, but this is a breakdown of or a cutaway of a typical IEEE 841 motor, which is the workhorse of the industry. It has a lot more enhanced features for protection. I'm not sure if you're familiar with the term IP. So this would be your typical IP54/IP55. I haven't put a bullet there, but just if you look at the shaft, you'll see a brass fitting. That's your Impro seal. And as I mentioned before, with TFC, you have a shaft-mounted fan. In this case, it shows sealed leads, which is all enhanced protection. There's a slide here. I think there's two little animations that I will advance. I'm not going to spend a lot of time on this because I don't want to run out of time, but these are the significant components you would see on the TFC large AC motor. Now, some of the commonality you'll find in motors. So I don't know, obviously, the level of experience and knowledge of people on the call, but NEMA stands for National Electrical Manufacturers Association. Some of this information is in the 4 handouts that you have. And I've identified here some of the critical dimensions. So when we're selecting motors or people are placing orders for motors, there's certain things that you need to be aware of, and that will save you a lot of headaches and time of returning motors that don't fit. The D dimension is probably the most important one, and that is the base to shaft center height. So that's from the bottom of the foot to the center of the shaft. The 2F is the spacing between the front foot and the back foot bolt holes. The 2E is the side-to-side spacing on the feet, looking at it whether from front or the back. The U is the actual shaft diameter. And then the combination of the BA and the NW is the actual front foot to usable shaft, or where the shaft starts. So if you're doing, alignment and knowing where the coupling is going to fit and how you bring things together, that's what you would need to know. A lot of people like to learn this little tip. So if you've been around motors for a little while and you hear people talking about, oh, it's a 184 motor or it's a 449 motor, like, what does that mean? Those numbers just made up out of thin air? Do they mean something? Well, in the NEMA world, they actually do mean something. So those first two digits, so if we're talking about a 449, forget about the third digit, but that 44, if you divide it by 4, you will come up with 11. And that is the base to center height. So whether it's a 180, you take that 18, divide it by 4, you'll come up with, I think it's 4.5. And then if you're getting into fractional motors, you take the first two digits and divide it by 16. My next slide will give you those examples. These are readily available, and if any of you carry manufacturers' motor catalogs, they'll probably have a page on this. And I find that, most people, it's like a gotcha. Oh, that's what that means. So what I haven't talked too much about is what happens after 449 frame. Maybe it was remiss, but low voltage motors are typically up to about 449. When you get above 449, you're in that sort of transition period between low and medium voltage. And just to put some sort of reference around 449, you're probably looking at about 250 horsepower in a 4-pole. And as I mentioned, the higher the poles, the more active material. So the number of poles and horsepower are going to dictate the frame size. Some other important things to know about NEMA frame motors, that often there'll be some suffix numbers at the end, or letters, I should say. So you might see a TD or TC, or if you see a Z or a Y. These are important things to note and point out. TD and TC are not usually a problem because those are to do with flanges. The ones to really be careful about is the Y and Z. These are custom changes to the shaft or custom changes to the flange. So if you're in a facility and someone says, go and get me another motor, it's a 284 TZ, well, you need to know what that Z is. We need the shaft detail, or manufacturer's going to need that shaft detail. Otherwise, you may end up sending it to the machine shop, getting something done, or sending it back. Just moving on quickly, one of the other significant questions that come up around motors is insulation. So what is insulation? Well, it's obviously the material that goes around the motor to help with its life. So a couple of killers for motors is heat and mechanical vibration. So heat is the big killer, so we need to protect that motor from being overheated, and the materials that go in there, they'll have a certain withstand temperature. The most common today is what we call a class F insulation, and that means that insulation is good for 155 degree overall temperature. I'm going to show you in the next slide how these temperatures are arrived at. So you may hear from time to time class F or class H insulation. Unfortunately, we do have these guidelines from NEMA MG1. MG stands for motors and generator. That's the Bible. That's the guide to buy these motors and how to manufacture these motors. every motor that you'll buy in North America assumes that the base temperature is going to be 40 degrees. That's not, you obviously know that not every motor is going to be subject to 40 degrees. Sometimes it's lower, sometimes it's higher. But to build up some commonality to arrive at these temperatures, we start off with a base temperature of 40 degrees. And on that, we start to add temperature rise. So class B would be, depending on service factor, would be an 80-degree rise, and then we add a 10-degree hotspot allowance or something for service factor. So when you add the 40, the 80, and the 10 is where we arrive at the 130. And if we do that with the F, add those numbers together to get at the 155. This chart doesn't show H. Another contentious, or well, I should say contentious, but an important topic is understanding hazardous area. So I'm going to talk quickly about Division 1 and Division 2. So in our world, typically we're going to be looking at the gases world. So Class 1, Division 1 is your explosion-proof areas, where, as I said, in Europe they call it flame-proof. But that's normally where there's a presence of explosive gases, either permanently or very often. Class 2, in this Division 1 Class 2 deals with dusts. Division 1 Class 3, which I haven't shown, deals with ignitable fibers.
Yeah, Karl, about 5 minutes.
Okay. So Class 1 Division 2, we show the gas groups. We're talking about minimum ignition temperatures. And so Division 2 Class 2 would deal with dust, and then like I said, Division 2 Class 3 would deal with ignitable fibers. This is actually one of your handouts, so I don't want to spend too much time out of this because we are slowly running out of time, or quickly running out of time. Just to indicate that there is a difference between the NEC and CEC. So as I've indicated here, NEC stands for National Electrical Code, and for us in Canada, think US. So that's the US code, which we tend to follow pretty much a lot, but there are some changes or some differences with the CEC electrical code, the Canadian electrical code. Understanding those are very much in the EPC world, and specifying motors as Canada's moving, or has moved, into a bit of a hybrid model of the European way of designating temperature and gas groups. So we use a combination of the zone system, and also in this slide here I can show you, or have shown you, that the gas groups are identified slightly differently. The only thing that's common between all of these different standards is the temperature code. So whether it's T3 or T2B. In Europe, they don't recognize suffixes, so it's only T3 or T2. In Canada, of course, we're going to be different. We actually have suffixes as well. So this is my segue slide into talking about variable frequency drive applications and motors. And we joke in our industry about the different nomenclature, different acronyms. So if you see or hear the word variable frequency drive, variable speed drive, adjustable speed, frequency converters, these all mean the same thing. Just very quickly, I'm not sure if you caught it, but we talk about, as we start to relate electrical to mechanical, so current is roughly proportional to torque. So the higher the torque required, the higher the current that's going to be needed. This is, I showed you this a little bit. I'm just going to advance a couple of transition slides. So a couple of my transitions. So as I mentioned about motor speed and the number of poles. So a motor in itself is fixed. We can't change the speed because we can't change the number of poles. But if we're able to change the frequency, then we can play with this formula. So this formula of 120 times the frequency divided by the number of poles, negating or allowing for slip. We can now actually change the speed of the motor. I'm just going to use my transitions. So as you can see, if we had a typical 4-pole motor that has a utility supply of 60 Hertz, if we change that utility supply down to 30 Hertz, that same 4-pole motor now runs at 900 RPM and not 1800. So that's the benefit and one of the main reasons for applying. So the only reason there, I could probably go into another 1-hour presentation about VFDs, but this is one of the big benefits of a VFD, is that we can now change speed and direction and control the ramp. One thing to keep in mind is that if you want to change speed, there is a limitation in the overspeed condition. A lot of people ask, well, can I run my motor faster? You can, but there'll be a trade-off. And because the current is usually limited, a VFD is, in all intents and purposes, a current limited controller. You won't really get more power out of that motor by increasing the speed. You can get more flow to a certain degree, but if there's a lot of back pressure, you won't. So general rule of thumb is you can probably overspeed a motor by 10% with no negative or detrimental fallback. And this really is what I'm saying is as you start to move up there, the motor is now really not going to catch up with itself, and you start to lose torque. This is almost a summary now. So the biggest question I get asked when I'm doing trade show events, or people come around and say, hey, what's the difference between VFD Duty and VFD Capable? Well, they actually are different animals. They are actually different types of motors. And NEMA MG1 addresses that. If you pull the standard, there's a part 30 and a part 31. The part 30 deals with VFD capable motors, which means that motor can run either across if you see in my notes there, it says DOL, AOL. The DOL stands for direct on line, the AOL stands for across the line. So that means that motor can be used with a normal motor starter, or it can be used with a VFD. VFDs will add a little bit of heat to a motor, so there's some other things and factors that are put into that. Now, a VFD duty motor is a dedicated motor that's intended to only ever run on a VFD. The characteristics of that motor are not designed to be connected across the line. And I've used an example here of, when you start getting to these very low turn down ratios, or hoists and cranes, where you may have to position and hold that load either indefinitely or for 5 minutes with no rotation. Normal motor will burn out. A VFD capable motor has features built into it to withhold and continue to hold that current in a stationary position. So I wasn't sure if I was going to get to this slide, but this is also one of your handouts. I use this as so basically reference material. I didn't get into standards in my presentation, but we can, basically this is my last slide. We can certainly go to the Q&A. I think we have maybe 10 minutes left.
Okay, hi guys. I'm just going to share my screen again. So we do have some questions. The first one was to do with credit hours, and that's for professional development hours. So we don't have the feature right now to generate certificates with our subscription level, but we've had that question a few times, and certainly there is merit to it. So we're going to explore that in future, and so we might have to bump up our subscription level to do that. But in any case,
you want me to chime in on that one? I think if you're talking about a PAGR or asset, I think you can have continuing education credits where you attend seminars and put it in your log, your notes. It might not be a professional designation, but I think you could say, yeah, I attended a 1-hour seminar. I think that helps with certain designations.
Absolutely, yes. This would definitely qualify for continuing professional development. However, we do have a lot of international people on the call, so maybe their associations are not self-regulated like ours are.
Okay.
So I don't know how some of the other countries run theirs. Perhaps they need some proof, perhaps. I'm not sure. So moving on, we do have some other questions about, okay, the 52 constant from Evans. And so and maybe I can see if I can find him on the attending list who can ask this question. But basically, I'm going to unmute him here, but he's self-muted. So he's asking whether the 52 constant, does it apply to both 60 and 50 hertz frequencies?
Yes.
Okay.
Yes, it does. And yeah, that's when you'll see a 4-pole motor, 1500, I guess I'm talking about. It does, absolutely, because it's how you calculate foot-pounds. But if you're in the IEC world, people probably want to know what the torque is in Newton meters.
Mm-hmm.
But you can do the conversion. Like, let's say, like on my computer, I keep a software, like a simple tool for doing conversion. So if you know one, you can calculate the other. But that constant will work both ways.
Okay, thank you. So Gabriel has left, but he does have a question here. I'll ask anyway. So when using a VFD to control motor speed, as frequency increases or decreases, what happens with the torque and the power?
Okay, that's a really good question. The best way I can try to answer it is that sometimes it's a function of the VFD, and I didn't get into the details between constant torque and variable torque. So certain loads, a constant torque load like a gearbox or a conveyor, as you slow it down, still needs all that torque available. So as I mentioned, the VFD is a current limited device, and the current is proportional to torque. So you could run something at half speed and still provide full current, so full torque. On a fan and a centrifugal pump, usually the torque varies by the cube, I think. I can't remember. So usually to move the same amount of flow or less flow, the torque requirement is less. So the VFD modulates the amount of current and torque generated, and the motor can do both depending on what it senses from the shaft into the VFD. So the VFD does have a certain amount of logic or back sense, and it can tell what's being demanded of it and adjust. I'm not sure if that answers the question well enough.
Well, it makes sense to me. Unfortunately, Gabriel's not on the line here, so I'm going to move to the next one here. I don't know how to pronounce this name, but Shreyas. So I've unmuted if you want to ask your question specifically, but in any case, I'll read it out. Just as a query on a temperature rise allowed, isn't there any margin as per NEMA MG1 for motor temperature rise by RTT method, basically for hotspot temperatures?
Yes, I didn't have a slide to show that. I kind of mentioned 10% hotspot. I'm not sure. Try back up. Yeah, there's absolutely some offset, and if you read the MG1, it'll talk about temperature rise measured by either calculated or measured by RTD, and the values differ by about 5 degrees, I think. So this chart here shows rise by resistance. So that's like a calculation from the resistance change, and then it could be rise by RTD, where you're actually physically measuring the rise. And when you put are usually when the RTDs are placed inside the motor, there's usually at 3 different points, and the intent is to actually put them in where you think the hot spots are going to be. So you want to try and make sure uniformity of temperature across the motor, but there is absolutely an allowance, and that's kind of what that blue bar on top is.
Okay, so we probably will go over the 1 o'clock time, but so I apologize to anybody that needs to go back to work, anybody that's on our mountain time here, but I do think there's value in going through all of the questions here, and we're going to stick around as long as there are questions, and they're going to be recorded. So if you have to go, you can always catch up and get the rest of these questions and answers later.
Yeah, let me just chime in. Yeah, lots of questions on VFDs, and we hope to have a VFD presentation in the future because, as Karl said, it deserves full treatment to explain the interaction of how VFDs work and how they interact with driven equipment.
Yes, that's true.
Yeah, I am very good for time for at least another 30 minutes, but if there are simple questions, I'm more than happy to field questions on VFDs.
Yeah, well, let's go through the list here. So the next one is from Anurad Chowdhury, and they're asking, what is the criteria for deciding combined VFD testing with motor?
If I understand that question, there is something called a string test. Now, very rarely is a string test required or requested for your common garden variety type motor VFD applications. String tests can often be done and may be requested at great expense on critical applications on mostly large machines. So with motors in general, let's just use the NEMA world, the T-frame world, the 449 and down. There's quite a lot of margin put into those and a number of assumptions. So the type of wire, and part of to get your CSA certification is to prove the design as well. So we talked about this offline in the RATS committee, but you will see nameplated information. We'll talk about the switching frequency, temperature rise. So generally speaking, depending on the topology of the VFD, some VFDs will add a lot more heating to a motor winding than others. Years ago, 20, 30 years ago, when VFDs started to come into play, motors were burning out quite frequently. Insulation systems have improved to handle what we call the dirty waveform, or non-sinusoidal waveform. And different manufacturers have better topologies or better performance on the output. But yeah, typically if you see a motor that's nameplated for VFD use, there may be some derating for temperature rise because they're going to shoot maybe a 10% additional heating. But it's well accounted for, and typically, as long as the supplier of the motor knows it's going to be on a VFD, they can kind of take that into consideration.
Karl, I've heard it recommended that if you're going to buy the motor and a VFD, it should be from the same manufacturer. What's your comment on that?
I don't believe you have to. I mean, it probably depends on the application, and probably maybe my answer would be different if we're talking about a 4,000 horsepower motor. But if you're buying a reputable motor and a reputable VFD, I would have no concerns. If someone came to me and said, I want to run, X, Y, Z motor, a VFD on your 100 or 150 horsepower motor, and if it's one of those top 10 or top 6 manufacturers, I wouldn't even flinch. I would say go ahead. Yeah.
Okay. So there's another question about temperature design ranges for North America for ambient temperatures. So they just want to clarify whether that's -40 to plus 40.
That's an excellent question. I'm trying to recall, but I think typically, I can't remember if it's minus 29 or minus 20 is considered the low ambient. And that's only really to do with maybe some mechanical concerns. The beauty of that question in a lot of ways is that you can actually maybe push your motor harder. Like, let's say there's been cases I've been involved in where somebody needed to run an application for 6 months or end the life of a plant, and they had a 300 horsepower motor. They wanted to run it a little bit harder. Well, the temperature rating was based on a high ambient 40. In this case, it was Nexon Long Lake, and we determined that 35 or 30 was really the high temperature of that location. So we were able to agree that we could push that a little bit higher because of the reduced high ambient. So if you have a motor that's sitting at minus 20, you have even more headroom or more margin or even more life expectancy. So the cooler you can run that motor, the longer life you're going to get out of it. So I think it's something like minus 20 or minus 29 is usually like the bottom end, and then you start looking at maybe some design changes for low temperature, or what sometimes we call Arctic duty. And a lot of it could be just a change of grease.
Right. Okay. Thank you. Just to let everybody know, I've unmuted everybody that has asked questions. So you can unmute yourself if you wanted to chime in. And this next question, I guess I don't think we're going to be able to answer it because I think this question is going to bring more questions to be able to solve a problem. So I'll read it out, and Ahmed Zab, if you want to chime in, feel free to. But they have a pump that's been driven by a motor which tripped after an hour of operation, and so I guess they tried twice, and the same thing happened. The pump was delivering the desired pressure, and the vibration was fine. And the motor was overhauled recently, and so he's just wondering, is that a possibility that it might be from the motor? And so I would say yes, but without knowing the situation, we really can't solve the problem, I think. I don't know if you want to point him in the right direction.
Yeah, so I've spent quite a bit of my career digging into looking at root cause and what some of those failure modes might be. And it's going to be a tough question to answer right now, but one way of checking a motor, and I know it's not practical in every sense, is to see how that motor runs uncoupled. So if you uncouple the motor, disconnect it, and then take a current reading, let's just keep it real simple. Let's say we're talking about a 25 horsepower motor, and if we use my example of 575, well, that full load torque and current would be about 25 amps, give or take. You might want to see what current's being pulled without the load. So, typically you probably would see no more than 2 or 3 amps uncoupled. If you're seeing something else, is that a misalignment? Is there something else? Is something pinched? Is something rubbing? Those are things you can look at. So looking at coupled current draw and uncoupled current draw will indicate some of the torque requirements. And even in the coupled condition, if you're seeing you're pulling 50 amps, maybe there's something else there. Maybe, yeah, I would look. It's one of the ways to look at it. Obviously alignment, things like that. But like I said, current proportional to torque, so you can look at that. I'm not sure if that helps.
Yeah. Well, the first thing that comes to mind when I read this, it says it tripped, but the pump tripped, or I'm assuming they mean the pump is tripped, not the motor. And my question is, okay, well, what do they have an indication of what caused the trip? Usually, you'll have some indication of what it tripped on, perhaps. And, maybe it might be from amp draw, it might be kind of vague, but, that would probably be the first place to start with, I think, if you know what the mechanism of the trip was.
Yeah, one thing I didn't talk about, and it could be a subject for a different presentation, but there is a limitation on how many times you can turn that motor on back to back. If you just sit there all day long, keep hitting that start button, you're going to burn out the motor. If something is causing it to trip, every time you start a motor, it absorbs heat. That graph I showed about the 600% inrush current, that's a lot of heat going into that motor. Unless that motor starts to turn, it has no way to dissipate that heat. So it could kill the motor eventually. So there is a cooling off period, and in large motors, they'll have safety devices or calculations or what it called number of hot and cold starts. And that could be programmed into the multi-lin. Yeah.
Automatic like safety, I guess, right?
Yeah.
Prevent you from starting.
So, yeah, and then just make sure, I mean, if it's taking out a motor and putting it back in and everything stayed the same, I mean, starters do burn out. I mean, starters have a thermal relay, thermal contact, and they can fail. But I'm not saying that is the cause, but a good electrician should be able to sort of determine that.
Mm-hmm. Yeah. Well, anyways, I guess that's certainly something to dig into, and if Ahmed wants some support with that, then Karl is available. He can also connect you up with somebody to help troubleshoot your situation if you need that.
Yeah, I mean, I don't know if this is a plug, but we talked about having panels. We could have a discussion around modes of failure and what different conditions are. You can have a repair NESA shop on that panel and have their perspective.
Yeah. Okay, so we're just going to move on to the next one here. Shreyas has another question about the DVDT allowed from the VFD across induction motor terminals as per the NEMA standard, if any. So I don't know. I'm just kind of reading it word for word. So if you want,
makes sense. The question makes sense to me. Okay. Again, that's something we should put into a future topic because it's getting into a lot more theory. And the DVDT is what happens. Let me just see.
Yeah, change in voltage over time. The speed of change.
Yeah. So if anyone's still looking at their screen, the picture I put in the left-hand corner is what happens with a pulse width modulated VFD. So you basically have a series of semiconductors that open and close to create an artificial waveform. So the picture on the left is a sort of an oscilloscope view showing all those peaks. The picture on the right is like showing it kind of more dampened out, so less resolution. So those peaks are the DV is change in voltage over change in time, and they put little impulses on the windings, and they can cause premature failure. There are some mitigations, and a lot of it can be related to lead length. So the problem can be exasperated or extenuated the longer the cable goes from the VFD to the motor. So it's a complex topic, and it's one worthy of a future presentation probably.
Mm-hmm. Yeah, I've heard there's just rules of thumb as far as cable lengths and wanting to put in a filter.
Yeah, and I'm not sure the person who asked that question, but one thing I would say is when we talked about VFD Capable and VFD Duty, the VFD Capable motor has an insulation system that's designed to handle a certain threshold of those DVDTs, and that threshold in 575 volt world, I think is something like, to be precise, I think it's like 1,897 volts. So that means that that there's a what we call a withstand voltage on the insulation system. So these little peaks accumulate, and they have a high voltage impulse. So the VFD capable motor have an insulation system to withstand a certain value of those DVTs. If they exceed that, then you have to have additional filtering.
Karl, Shreyas here from India. Just to add on to that, the query was because of the PDIVs that the motor needs to be designed for. So I just had a query on what would be the typical dV by dt value in the industry, whether it is 10 kV per microsecond, or just an example of how you've seen for example for a 50-meter cable length.
To be honest, I don't know if I could pull that number out of my head right now. You talked about PI, like the potential discharge. Is that what you mean?
No, it's partial discharge inception voltage is what I'm speaking of.
Yeah,
For
okay.
PD measurements.
Yeah. To be honest, I'd have to get back to you. I've seen it. I just haven't memorized it. Yeah.
No problems. Thanks.
Yeah, and I think I think some VFD manufacturers may publish what their inception voltage is at certain cable lengths. I've seen it. I mean, I did work for a VFD manufacturer in a previous job. I just don't remember those numbers off the top of my head.
Thanks.
Yeah, thank you very much. So there are just a couple more questions that I see here. So Sanjay Sharan, and you can always unmute if you want to add in. The question is, at our gas processing plant, there's more and more frequent failures of motors of 800 kilowatts to 1.1 kilowatts, or maybe they mean megawatts. So just wondering if there's any particular reason why they're seeing that.
Well, that's going to be hard for me to comment.
That's a loaded
or speculate
question.
on. Just
Sanjay, do you know that?
Yeah, I mean, if
yeah, actually, this gas field is a sour gas field, the largest gas processing complex in Asia, in India, in Gujarat, Surat. And we find that possibly the dust conditions or the cooling conditions are not that good. And possibly we are still not using the closed motors. Mostly these are the open motors, and they are into applications into the sulfur recovery units, or maybe the areas where we have more dusts coming in. But possibly, I mean, as a mechanical engineer from the quality assurance side, I would really be very helped if we could get some technical understanding of the failures and get to the root cause analysis of failures, some methods, or some preventive measurements or preventive activities that our team should be taking up in arresting these failures.
Yeah, I'm glad you added to the question, because it makes a lot more sense to me now with that additional information. So if you have an open motor of some description, you can have buildup on the windings. So you'll get contamination. You may start to get partial discharge or other things, other burnout conditions. You may have electrical failures on the windings because of contamination. There are a number of different maintenance things that you can do, and depending on the voltage, there's also some tests that you can do to look at partial discharge. It sounds to me, from what you've just told me, that you're having electrical failures and the motor windings are burning out early, or maybe within 2 years of going back into service, or 3 years. So it sounds like cleaning. I mean, you can clean those. I don't know if in your area if you have access to dry ice, but there's a lot of companies that use dry ice cleaning, like CO2 dry ice cleaning, which doesn't have any caustic or or any negative effect. You can clean electrical equipment with dry ice. But there's definitely some testing that you can do to try and avoid it before it fails unexpectedly.
Thank you. Thank you very much.
Okay, so Yazim Al Hinai has a couple questions. If the VFD got some failure in running the driven motor, what are the consequences on the motor?
Well, again, it's the mode of failure, and if we, we wouldn't know off the top of our heads whether or not it would be the VFD causing the failure. Usually,
Right.
the VFD acts as a motor protection device as well. There's many advantages to a VFD that can actually save the motor before it goes into a catastrophic failure. So understanding what the failure is, I mean, it could be that the motor isn't a VFD rated motor, but normally a VFD will have a current limit, a program switch turned on in it, and maybe it will trip at 150% overload. There's other features that you can get in VFD firmware and software that can give you all kinds of feedback. I mean, there's lots of real-time data logging going on in VFDs. So I'd have to know more about what the concern was and why you feel that the motor's failing on a VFD. Does that help? I don't know if that's an answer or not.
Yes, Yazim, you're online here. Did you want to add to this at all? I'm not sure if I'm pronouncing your name right.
Can I understand what is the true center and the magnetic center of a motor? Because from the vibration analysis angle, they say that once the motor's magnetism has come in, it shifts either towards the coupling or away from the coupling, and that sometimes leads to axial thrusts or maybe some vibrations in the X and Y directions also.
Okay, so to put that into context, are you talking about a sleeve oil bearing that floats, that has the ability to?
Yes.
Yeah. Okay. Great.
Yes.
Yeah, because usually that question would not be a concern on a ball bearing or a fixed bearing type motor. And a sleeve, for those that may not be familiar, but on large motors, when you get up in 2,000 horsepower plus, especially on 2 poles, it's considered a good investment to use sleeve oils. And I'm sure most people probably are familiar with sleeve oils in one fashion or another, but it's a hydrodynamic bearing that floats on a film of oil. And when you energize a motor, it's going to lift up from its stationary position and find its optimal place where it's magnetically happy. And on most motors that I'm aware, in initial setup, there should be an indicator on the driven shaft with a couple of scribe lines. There will be usually 3 scribe lines machined into the shaft, and the center line usually represents magnetic center with usually a slim metallic sheet metal arrow that for setup allows the millwright or installer to know where to position the rotor prior to connecting to the coupling, so that when it is coupled, it's not fighting against its natural set point. So usually that float, those manufacturers would probably put a value of how much float there may be. So I can't speak for every manufacturer, but we're talking about, I mean, like less than 5 millimeters, a certain amount of float, maybe a bit more than 5 millimeters, but could be 10 millimeters. Again, it depends on the length of the rotor and stuff like that. But you should have an indicator to show you where magnetic center is, a mechanical indicator where magnetic center is. And the other thing would be to set it up. If you don't have that already on site, if you had it uncoupled, run it, and then make a notation of where that end of shaft is, and align it like that afterwards.
Thank you.
Does that help?
Thank you. Yes, yes, that was helpful. Yes.
Okay, so well, thanks for everybody that's sticking around. We got just one more quick question. It should be quickly answered, and then we can conclude. So if the motor's designed for 60 hertz, can it run in 50 hertz?
Yep. Yeah, actually it can. Performance will be a little bit different, but yes, the short answer is yes. I mean, if you had a motor data sheet, like a performance sheet that shows you how much torque and current, I mean, those values would be different, but there'll be no detrimental effect to running it at a different frequency. No different than, if it's like we talked about VFDs a lot, so it'd be like taking a 60 hertz motor and running it at 50 hertz on a VFD. But yes, you absolutely can, as long as the voltage isn't exceeded. You don't want to put a 230 volt motor on a 400 volt supply and then change the frequency.
I've never considered doing that before.
Yeah. Yeah, but it's for sure. And we see this often on OEM equipment that comes into Canada. Like I know, for example, in Central Alberta region, lots of dairy farms, right? Lots and lots of dairy, and a lot of that OEM equipment comes from Europe, particularly Holland. So yeah, you'll find 50 hertz motors all over the place.
I would just add, yeah, if you're running some critical equipment and it's tested at 50 hertz, it might do something different at 60 hertz. Now the motor may be fine, but your driven equipment might behave differently at 60 hertz because of the different speed it's running. So you would be good to specify that you want your equipment tested at the 60 hertz speeds. Particularly if it's coming from a country where they normally run at 50 hertz.
And again, it depends on what size of motor we're talking. I keep thinking small motors for this topic, but if we're getting into 1500 horsepower, 1000 kilowatt motors, then yeah, we want to be a little bit more critical, a little bit more analytical about what we're looking at and what we're saying is good.
Well, I think that concludes our longest webinar so far, and it's been fantastic. There's a lot of great questions, a lot of great answers. I think there's a lot of value in going through this. Thank you very much, Karl.
Well, I've certainly enjoyed participating. I want to thank the RATS committee in Edmonton for putting this on, and I just want to say, if you liked what you saw, I hope you go on to TripAdvisor and give me a 5-star.
Absolutely.
Thank you, Karl.
Any closing words, Ralph?
It's been very good. I would say most of the audience here are all mechanical, and electrical is often kind of a mysterious area, and this certainly helps our understanding of electric motors. So yes, thanks very much. And so there's a survey following this, so you'll also get an email as well. So let us know how we did. Let us know if there's anything else you want to hear about. And again, your interest level in a specific VFD presentation on its own. Again, we could probably have another one all on control panels too. But anyways, we're signing off for our 5th webinar, and have a good day or night.
Thank you.
Thank you.